And the Force is what gives the Jedi his power. It's an energy field created by all living things. It surrounds us and penetrates us. It binds the galaxy together.
Maneuvering thrusters, Mr. Sulu.
Greetings, cadets.
Maneuvering thrusters. Hold station.
We finished prototyping our sketch and tweaked the settings so that it runs the way we want. Now our ultimate goal is to upload the sketch for our Starship to an ATMega chip and run everything independently of the Arduino UNO. You'll remember from our first lesson that the Arduino has various built-in safety measures to protect the ATMega chip from real-life hazards such as voltage surges, current overload, and accidentally reversing the polarity by swapping the positive and negative terminals. In the same way, we would like to protect our programmed ATMega chip as much as possible once it is placed into a permanent circuit. To do this, we can actually prototype a power supply which has some of these nifty protective elements built right into the circuit. So, without any further ado, let's get cracking. To start with, we need the following components: a breadboard and some jumper wires. This time around, we don't need the Arduino UNO. We also need an input socket for our new power supply in the form of a barrel jack, as well as a mini slide switch and a PTC resettable switch. These three components are optional and can be left out if we prefer. We will have a look at a more simplified version of this power supply at the end of the segment, where we omit these components completely. The vital parts for the power supply to function are an N4001 rectifier diode, a 100 microfarad capacitor, a 10 microfarad capacitor, and of course an LM7805 linear voltage regulator. So let's put it all together and build a super safe 5 volt power supply. We'll start with the barrel jack socket, which is the socket into which we plug our external power supply. Our external power source should be an AC power adapter capable of outputting 9 or 12 volts with a current of at least 2 amps if we plan to drive a lot of LEDs. In order to know which output pin on the barrel jack would be positive and which one negative, we need to look at the specifications on our power supply. Every power supply will have the strange symbol included in the specifications. In this example, it shows us that the inner core of our barrel jack is positive, while the outer sheath is negative. This is more or less the standard setup, but sometimes one will come across an AC to DC adapter where the reverse is true. Reversing the current by accident will fry the ATMega chip instantly, so it's a good idea to build a protective measure to prevent this. The leg at the back of the socket connects to its central pin, which in our case is positive, while the leg on the side connects to the negative sheath of our barrel jack. Sometimes, however, it may be the other leg that's negative, so it's best to test them first before wiring them up. We can solder some header pins onto the legs of the socket, which allows us to insert it into a breadboard, so that one row of our breadboard is positive and another negative. Next, we add a small switch to the breadboard. We'll be using a mini slide switch, designated as SS12D00G3 on eBay, which is a single pole double throw switch, and, most importantly, it works within our required parameters. We connect our positive voltage to the central leg of the switch, and when the switch is closed, the current can flow across the opposite leg of the switch. The only disadvantage to using this switch is that it can be flipped in the opposite direction too. This could cause power to accidentally flow in the opposite direction and create a short circuit. To eliminate any possibility for this scenario, we need to cut off the redundant leg of the switch to prevent contact with the breadboard. Thanks to the eagle eyes of Aircool for pointing out this potential problem. We add the switch to the breadboard in such a way that the central leg is in the same row as the positive leg of the barrel jack. This means that power can flow to the outer leg of the switch. Once the switch is closed in the on position, power can flow across to another part of the circuit. Let's connect the LM7805 linear voltage regulator. As we can see, it's capable of functioning within our specifications. The 05 at the end of the number tells us that its output is 5 volts. In essence, our external input voltage enters the voltage regulator by its left leg and gets down-regulated to 5 volts, which is output via its right leg. The center leg is the ground leg, and just like a MOSFET, it is an extension of the back part of our voltage regulator, to which we can attach a heatsink or create a grounding point for the rest of our circuit. We insert the voltage regulator in the opposite side of the breadboard in such a way that the back silver part of the regulator faces away from the power socket, which means that the input leg, ground leg, and output leg will be on different rows of the breadboard. Next, we add a 4001 rectifier diode which can handle our voltage and current loads. In the same way that an LED has a positive leg and a negative leg, because it's essentially a diode which emits light, our diode needs to be inserted the right way around. The stripe on the circuit diagram represents the stripe on the side of the diode, and voltage flows towards that stripe from positive to negative. If the polarity of the circuit gets reversed, the diode will not allow power to flow from the opposite direction. This is our ATMega chip's protection against bad wiring or using a power supply with an incorrect polarity. We insert our diode across the gutter in such a way that the stripe faces in the same direction as the back of the voltage regulator. Our next component is the PTC resettable switch. This is a handy gadget as it limits the current of the power supply we're building to 500 milliamps. This is the safe current at which the Arduino UNO normally operates. It is called a resettable switch because if the current suddenly goes higher than 500 milliamps, like in a power surge, the switch cuts off the current flow to the ATMega until it drops to 500 milliamps or below again. This type of protection is also built into the Arduino UNO board, but it's entirely optional in our circuit, as the power supply circuit will work just fine without it. We insert the PTC in such a way that it connects our diode to the input leg of the voltage regulator. Next, we'll add the 100 microfarad capacitor. A capacitor also has a positive leg and a negative leg, and, like the diode, the stripe on the capacitor tells us which leg is the negative one. We insert the positive leg of the capacitor in the same row as the input leg of the voltage regulator, and the negative leg in the ground row. The smaller 10 microfarad capacitor gets inserted on the other side of the voltage regulator, with the negative leg connected to the ground row and the positive to the output leg of the voltage regulator. The capacitors help to smooth out the power flow to give us a nice stable 5 volt output. We connect the 5 volt output row to the positive rail of the breadboard and the ground row to the ground rail of the breadboard. All that's left is to connect the ground leg of the voltage regulator to the ground leg of the barrel jack socket using a jumper wire. A useful feature in the circuit is that it has a very small footprint on the breadboard. It only occupies 4 rows, which leaves plenty of space for other circuits on the board. Let's trace the current flow in our circuit. The input voltage enters the circuit via the central pin of the barrel jack, and once the switch is activated, current flows via the input jack across the closed switch to the diode. It flows across the diode from its positive leg to the negative one, and then across the PTC. If a current of more than 500 milliamps tries to enter the circuit, the PTC cuts off the current flow at this point and only resets once the current is at 500 milliamps or less. The current flows across the leg of the capacitor, and the voltage gets converted to 5 volts by the voltage regulator. The 5 volts flows across the jumper wire to a positive rail on the breadboard, where it can safely power an ATMega chip. The ground rail of the breadboard is connected to the ground leg of the voltage regulator, and via a jumper to the ground pin of the barrel jack, which is grounded by the external power supply. When we plug our power supply into the input socket and flip the power supply switch to the on position, the current flows across the components to the voltage regulator, where it gets converted into 5 volts. If we slowly increase the input voltage to 12 volts, we notice that the output voltage is not affected and remains at a reading of 5 volts regardless of the higher input. A voltage regulator has a minimum voltage below which the output voltage is no longer a steady 5 volts. This is known as the threshold voltage. Anything below 7 volts causes the output voltage to drop erratically. However, at 7 volts, the output returns to a steady 5 volts, where it remains even at higher input voltages. This circuit is great for creating an ideal environment for the ATMega chip, but we need a higher input voltage to run things like the sound, interior lighting, and the LED strips for the nacelles. This can be accomplished by connecting the positive input of the barrel jack directly to another positive rail, and the ground rail directly to the negative leg of the input jack. To demonstrate, we connect the multimeter to the positive and negative legs of the barrel jack before the current flows through the rest of the power supply circuit. We notice that the voltage reading on the multimeter is the same as the input voltage from the power supply. When we change our input voltage, the reading of the multimeter changes correspondingly with the input voltage. As an option for a real bare bones power supply, we can omit the barrel jack, the power switch, and the PTC switch entirely. After we connect the diode directly to the input leg of the voltage regulator, we can use jumper wires to connect an external power source directly to the breadboard. Now that we have built a fairly decent power supply, we are one step closer to creating an independent circuit. Next, we'll learn how to program the big ATMega chip so that it can run the sketch we originally uploaded to the Arduino UNO. But until then, so long and thanks for watching.